Hey, John here. Let's have a quick look at how shared memory works and what does it really mean, okay? That means that you have memory that is shared, what, between two address spaces. Okay, now what the heck does that mean? Well, let's start with a simple example. Let's say I want to run a program, and that program is commonly used. Maybe I want to run 3 copies of the same program. Now, I can do a couple of different ways. If I'm the operating system, how do I want to manage this? Well, I can create a virtual address space for process 0, and I can create a virtual address space for process 1. And what's going to happen? If these are running the same program, 2 copies of the same program, what does that mean? It means that the text in each of these programs is 100% identical. Oops, I forgot the BSS in there, but you know what I'm talking about. I'm not going to start over again. He grows up, he grows down, and so on, right? The point is, let's say these are big programs. So let's say there's like a megabyte, right, of text in here. All right, it's big. It's a big program. It might be a web browser, right? Open up another web browser so I can have 2 of them on my screen at once. Those are big programs. It would be very nice if the operating system didn't keep 2 copies of this, all the data in this executable text region for both of these processes. All right? Now remember, these are virtual address spaces. Virtual address space, okay? And we look at the physical memory. All right? What happens here? If I have 2 separate processes, let's work from the top down. This guy's stack is going to be in 1 or more pages up here. His stack is going to be somewhere else, right? They're not going to have the same stack. That doesn't make any sense. The heap is going to go somewhere, right? This guy's heap goes somewhere. His data goes somewhere. This guy's BSS and data go somewhere else, right? So this is, I'm going to say like this. And he's going to go down here, right? So there's a bunch of pages for each of those regions, completely independent, all right? They're going to sit like this, in other words. This guy's not going to share anything with this guy over there. However, when it comes to the text, if this guy's got a whole bunch of pages of text, why can't they be the same pages that this guy uses? Right? We save a lot of physical memory because, you don't modify this as it goes, or you certainly shouldn't, okay? So it turns out all this here can be shared. And what is shared is executable content that neither of these processes is ever going to modify. Now, we're going to just trust these 2 processes that they're not going to modify? No. We are going to force them not to modify that because there's something else that the MMU can do. In addition to mapping all these pages from virtual addresses to physical addresses, they can put other flags in there, right? So let's look at the page table. All right, let's just assume it's a single level page table lookup. Normally they have multiple levels and stuff in here, right? So what happens in here? For this address space, there's a bunch of page table entries that describe the text region, some page table entries that define the data, and so on. Down here, or wherever the text page table entries are going to be, we can mark them not only as valid, but we can mark them as read only. Almost every virtual memory system these days has other flags than valid in there. If it's valid, you can say whether it's read-only or not. And if I mark these as valid pages and I mark them as read-only, then I know no matter what this process does, even if it tries to modify the data in these pages, he cannot corrupt this memory, which would cause these other processes to die. All right? That's really nice. What other flags are common in here? Well, it can also have an executable flag. That's nice too. So these pages would be valid, they'd be read-only, and executable. More specifically, the pages that represent these other areas of the code are not executable. And they would be marked for read-write. So these would be valid, read-write. Okay? And these would be marked for no exec. Right? Same, all of these. Valid, read and write, and no execution, right? Now, why would you care about the execution in here? You want these executable. You don't actually want these executable. What if there's an error in this program down here that causes you to branch up here? Okay? Now, if you branch into the middle of nowhere, this is kind of like no man's land up here, you get a seg fault, because the operating system would say, oh, you're not supposed to touch this memory in here. Why? Because that memory would be marked as invalid, and it would kill your process. Okay? Well, what if you branch into the middle of your BSS? That memory is valid. There's nothing about the system that's going to stop your program. And what if the BSS had a bunch of data in it that just happened to have values that were legal instructions? You would then be executing garbage instructions in here by accident. Okay? But if I instead mark the pages where I map the BSS as being not executable and I branch up here, it'll stop immediately, regardless of what happens to be in these memory pages. Even if it was valid code and I wanted to execute it, it would stop it because it would be marked as not executable. Right now, there's all kinds of flags and things that you can set for processes, and when you build the operating system, do you want to enforce these rules or not? Or do I want to be able to allow the instructions in here to be modifiable? We call that a self-modifying program. Okay? You can turn these things on and off, but that's more advanced features. I'm not going to go into that. Just know that it's possible, although not a commonly used thing. So, shared memory can speed up the time it takes to start up a new process. If all the executable code is already in the memory, all I need to do is create this address space, fill in my page table, and the only thing I need to initialize are these parts up here. I don't have to initialize the text part. Okay? Turns out it doesn't really have to initialize anything for the heap and stack because they start out empty, right? The BSS is simply zeroed out. That's pretty fast. And the data region is actually part of the executable file image along with the executable text region. There's a copy of the initial data region in the file that holds your executable program. So rather than reading in all of this off of disk, it only has to read in this much of it, all right? So that speeds things up. And it saves me memory. So what other reasons we need to use shared memory? Well, on a Unix system anyway, it's very common to run a command like this. You would say something like, maybe I want to know, I got a file. It's called a file X, right? And I want to know, maybe it's full of text, and I want to know how many lines in this file has a pattern like a word ABC. So I can say grep ABC file X. What does that do? It'll list on the screen, it'll print out every line of this file that has ABC in it. That's nice, and then I could go back and count them. If I was, a new guy, I might do that. If I know what I'm doing, I would pipe it to word count minus L, all right? This is a program that just simply says, here's how many lines of text were given to me. So it takes the output of this command and sends it to the input of this command over here. So if I type this in, this word count program would print out how many lines were printed by the grep command, which would be how many lines in file X has ABC. That would answer my question. How does that work? Well, it turns out when I start the grep command, so this is my grep, right? This is my virtual address space for the running process for grep. Because I put a pipe in there, the operating system says, okay, I'm going to fire these two up. Here's my word count minus L, the virtual address space for that. Okay. Text data, BSS, heap stack, and all this other fun stuff. Part of each of these two processes in maybe the data region, it turns out it's not there. There's another region for this, but for simplicity, part of what we're going to see is shared data between these two processes is the buffer that it's going to use in here. These two things are going to have one or more pages out of the physical memory that are going to be mapped into each of these two processes. So just like a shared library, this is shared data. So I might have multiple pages. It doesn't really matter. You can have more if you need more shared. But what happens is if you use a pipe, and this is a really simple description of this now, okay? So don't burn me on this. Yes, this is done in a more sophisticated manner, but in the most simplest terms, conceptually speaking, when this one runs, rather than printing its data on the screen, it ends up getting put into memory in these shared pages, okay, by this guy. And this one over here reads the data out of there instead of reading from the keyboard. This allows data to flow directly between these two processes. And then when it's done, this one will print out. I saw 20 lines or however many there are, okay? Now, I'm glossing over a whole lot of other things that has to happen in here, like how does this one know that it's not written too much before this one consumes it? How does he know that he wrote anything at all? Because it's just bytes in here. How long does he wait for this one to fill it in? That's a whole nother ball game, all right? And that is solved by something called semaphores. All right? These things allow two processes or more to be able to be synchronized. All right. And if you're going to use a pipe, you're going to have semaphores in here. So this thing doesn't read all this garbage data before this guy fills it in. All right. I'm just saying there's more to this if you're going to implement it for real. And this is a really simple example of the kind of thing that you might use shared data for between two processes. You can yourself in your program, you can just say, hey, I want to allocate some shared memory. And another process can come along and say, hey, I want to use this same memory that this guy over here is shared. All right. That's, again, like a semaphore. It's a resource that the operating system provides that as long as multiple processes collaborate, they can find these shared pages and map them into their virtual address spaces. And with semaphores and other mechanisms, they can both read and write data and see what's happening in the other process. All right. So this is another kind of shared memory. Now, before we go, let's look at one other kind, right? Just like when we shared two processes shared all the same text region because they're running the same command at the same time, you can do a subset of that in what we call a shared library. So let's say I have two programs. In each of these programs, they're unrelated programs written by different people in every way, shape, and form. However, let's say they both, in their text region, have a gigantic graphics library. All right, bunch of code in here. They're both programs that draw graphics and stuff on the screen, right? You don't want to write all that out, so you got a library in there. So here's your text. This is my text region. And this is full of a bunch of instructions for some programs. So maybe you got X, whatever instructions in here. Why? Because this is program X. Here's another program. It's program Y. Well, what's in his text region? The instructions, why, right? But this stuff is the same. Only this part. And let's say this is, 5 megabytes worth of data in this library. Well, obviously, if we're creative, the physical memory of the machine can be used such that the pages for the graphic library, and only those pages, can be the same pages and shared across 2 or more processes at the same time, while the rest of this text region, the pages for this, are different than the pages for this. Now, there's a lot of implications here, okay? You have to, when you compile these two programs, you have to tell the compiler, I'm going to use a shared library. And what it'll do is it'll make sure that it puts the library in a place inside the text region so that it fits exactly into an integral number of pages, right? You can't have, remember, all this stuff is based on page boundaries in here. So if I'm going to share a page, I share the whole page. I can't share half a page. So this text region here has to be built such that the graphics library fills an exact integral number of pages and starts at an address that's a multiple of the page size. Otherwise, it just can't be done. Okay? Now, depending on the kind of shared library, you might have to have this library running in this virtual address space at a different virtual address than it runs in this program. Okay, so maybe the address of where the graphics library here is 222,000. And over here, it just so happens to have to run at 333,000. Think about that. The instructions in here that need to branch around and stuff like that kind of have to have some way of knowing where to go and where things are. And if it's running in this address space at a completely different address, then the exact same code is running in this address space, then this code has to be written very carefully, okay? So if this code ever refers to like a branch instruction, and it says, I want to branch from here to there, when you write this and it's compiled, the compiler has no idea what address it's going to or from. So in order for that code to work, when you compile this sort of thing, you say PIC, okay? Position, independent, code. If you're going to create a shared library and you want maximum flexibility, the code that comes out of the compiler has to be position independent. In other words, every reference from anywhere to anywhere else inside this chunk of pages, inside that shared library, has to be basically program counter relative. Right? Because there's one thing you know for sure. If this instruction right here is executing, and it needs to move 200 bytes up here, well, that's 200 bytes from the current program counter. Right? It doesn't matter what the like if you put a label on a statement, like if this was written in assembler or something, that's irrelevant. As long as when it's all said and done, the actual instructions used refer to this target address by using a program counter relative offset, and then it works fine. All right, now there's other gotchas for data labels and other such things, but there's solutions for those too. We're going to save all that for another time. In the simplest of terms, we can share part of a text region or all of the text region, right? For the case where we have the same program running twice, okay? We can share data regions for multiple reasons. Okay, if you're going to use a pipe or you just want to write a piece of code that has a shared memory region up here, that's going to be shared with some other address space over here. And again, they don't have to be at the same virtual address in both of these address spaces, right? If they just have to be shared, that's all you need to worry about. Okay? And there's ways that the operating systems provide. Says, I want to allocate a shared memory page. This one might say, hey, I want to use a shared memory page that someone else already allocated. Okay, so we can have a conversation through there. All right, so these are the basic types of shared memory, kind of why you'd want to use them in 10,000 foot view here, and how it works. It's all based on how you fill in your virtual memory page translation tables. That's how this whole thing works. All right, so thanks for watching. See you next time.